Hello and welcome to the course Introduction to the Psychology of Language. I am Ark Verma from IIT Kanpur and we are running in the 6th week of the course. We are talking about reading, various aspects of it in this course. Today we will talk about a specific aspect of reading, that is recognizing visual words. So when you see words, how do you really make sense of them? Do you, say for example, as we were discussing in the last lectures, immediately are you immediately able to convert the grapheme into phoneme and kind of make sense of what a word is and then move on to lexical access and making meaning? Or say for example there are other processes that you might need to do. How is that really accomplished? That's basically what we are going to look at in today's lecture. Now reading a word involves taking the perceptual input, that is the visual impression of the word, and using it to recognize individual words and kind of from that move to lexical access and understanding word meaning. There are two kinds of models that have been sort of generically proposed with respect to how people accomplish word recognition, and basically these are called the dual root and the dual root cascaded models, and then the single root models, which are more from the machine learning neural networks sort of domain. So let us look at the models. First, let us look at the dual root and the dual root cascaded models. Now, the dual root accounts are probably the most extensively investigated accounts of visual word recognition. These models are called dual root or dual root access cascaded models because they propose that there are two separate pathways, there are two separate routes using which people can use the visual input to recognize individual words. So, say for example, in one of the ways you can just sound out the given word, that is converting each of the letters to its sound and then kind of combining all of those sounds and then speaking it. Or say for example the other way is a more direct way, you look at a word, you directly map it with something that you already know and you kind of use that as a way to read the word. In detail, let us look at, say for example, in the first model, that in the first root, that is the sounding out root, what you will need to do is you will need to kind of get to the sound of each and every letter in a particular word. You need to concatenate those sounds, attach those sounds together and then create a phonetic phonological version of the word and then use it to perform lexical access, reach to the form and then later reach to the meaning. This is basically called the grapheme, this is basically called the indirect route or the phonological route. Okay, basically it uses what are called grapheme to phoneme conversion rules to reach from letter configurations to the sound configurations. But it's not really very straightforward. I mean if you kind of think that I am saying that you will very easily use these letters to convert them into words, into sounds and then speak the name and following something called the grapheme phoneme conversion rules, we really need to also talk about whether what these rules are and whether they are very easy to apply. Now, one of the things that is very peculiar to English or some of the other orthographies as well is that there are both kinds of words in English. There are regular words in English and there are irregular words in English. What are the regular words? The regular words are wherein a similar grapheme to phoneme conversion rule can apply and it will lead to a similar kind of a sound generation. The irregular words are where you cannot really apply the same rule to get the same kind of sound. Let me give an example. Say for example, mint is mint but pint is pint, or say for example to is to and go is go. HAVE is have, whereas SAVE is save. So you see that there are multiple of these instances where the same configuration of letters will not lead to the same configuration of sounds. Now if this is the case, the phonological route will not really be always effective in creating a reliable and a consistent sound based representation or a phonological representation of the incoming visual word, of the visual word that you are trying to read. Now this is basically something that can lead to second language learners of English into making mistakes. Also initially kids, when they are learning to read, they would also make these kind of mistakes. Now the mistakes that people sort of make in this in this route basically are referred to as regularization errors. What are the regularization errors? When the assembled phonological root remains active and sometimes leads to mispronunciations, that is called regularization errors. Okay, and what is the other way to do this? The other way is actually when you come across these exceptions. Yesterday I was talking to you about BOUQET pronounced as bouquet and PSYCHO pronounced as psycho and not as psycho, something like that. So how do you really read those kind of words? Now for those kind of words, the dual root models specify a particular separate root, which is called the direct orthographic root. The direct orthographic root basically matches the visual code directly to a lexical entry and makes the correct pronunciation available. You do not need to assemble the phonological root. You will not assemble the phonological representation by combining each letter and creating its sound, because if you do so, you will lead eventually leads to particular kinds of errors. The errors would be of the kind that I just mentioned, the regularization errors. Suppose if you are kind of using the assembled phonological root to read some of these exception words, then you will obviously fall into mistakes, and those mistakes will be called as regularization errors. Also, however, the direct root cannot be used for everything, as the GPC roots will help us generate sounds also for newly encountered words. So for example, if you are reading the first a word for the first time in your life, suppose say for example you come across a word like psychology, or say for example there are also interesting words like genre, genre, So for example, if you're coming across these new words and you've not heard them being said earlier, you are more likely to use the assembled phonological root and then come up with incorrect pronunciations. So the direct root can only kind of make available correct pronunciations for words that you already know or for words that you've heard earlier in time. That is basically what this looks like, and here I can show to you the dual root cascaded model of reading. This was put forward by Max Coulthard, Cathy Russell, and Perry and Langdon and Ziegler in 2001, and this is how the model looks. You can see the model starts at the top. You are looking at something in print, then basically you will carry out an orthographic analysis, basically looking at what is this word really composed of, what are the letters and so on, and then once you have that, you will basically carry out what is called the orthographic analysis, and you will either move to the orthographic input lexicon, wherein you kind of analyzing each of these letters, you kind of then doing the phonological output lexicon, you're carrying out the GPC conversions, and basically you are so basically you are then reaching a response buffer. So this is the path on the right: orthographic analysis, grapheme phoneme rule system, and response buffer. So you convert that and you reach the assembled phonology. This is called the assembled phonological root. The one on the left basically is the system that kind of is the direct root. So you do go to the orthographic input lexicon, what are the words that I know of, and then you kind of directly have the phonological output lexicon. It directly gives you the correct phonological output, and then it can go to the response buffer and you have the speech. You have sort of also a unit called the semantic system that is attached to the orthographic analysis, because it kind of simultaneously activating entries. As soon as you are reading the word, this is activating entries in the semantic or the meaning system at the same time. This is basically what is called the dual root cascaded model, because the flow of activation in this model is in cascaded nature. As soon as you start doing the orthographic analysis, the phonological and the semantic analysis are already started. Okay, so that is basically why this model is referred to as a dual root cascaded model. Now let us go into a little bit more detail. If you see in the assembled phonological root, the GPC root basically, or the grapheme phoneme conversion path postulates serial activation of phonological code of letters. Say for example, if I have to read play, PLAE, PLAY will kind of be generated in a sequence. Now the evidence for this, the evidence basically is, say for example, if you see, the DRC route predicts longer longer reading times for irregular words like pint, kernel, etc. If the GPC routes, if the GPC conversion had to happen serially, left to right irregularity at the beginning should cost more in terms of time as compared to to the irregularity in the end. Now, what am I actually saying? I am saying is that if you were to read these words in a serial manner, as the GPC thing is saying, the irregularity in the beginning of these words, because you are converting, will prove to be more costly as if the irregularity is the end of the word. So, basically, and that is exactly what is found. Say for example, if you were read a word like choir, CHOIR, you will find that it is harder to read than benign, BNINE, say, because benign, the irregularity is more towards the end, and in choir the CH is being pronounced as K is in the beginning. So, this is one. Now, this is also not completely alright, because say for example, the DRC predicts that words with visual uniqueness points should be read more quickly than those with which have later visual uniqueness points. Say for example, dwarf, the visual uniqueness point DW is earlier, and this is read slower than carpet. This is the prediction of the model, which is not really confirmed by the literature. So, not all the assumptions of the dual root models are kind of found to be correct, and obviously then that is why there remains scope for more research and more understanding of the processes involved in visual word recognition. Now, let us move to the single root models. The single root models basically have grown out of the tradition of parallel distributed processing, and basically they are based on neural network modeling and so on. They typically contain three kinds of units. They contain orthographic units, which represent the orthography, the written version of the letters. They have phonological units, which contain the sound representations, and they have semantic units, which represent the meaning based representations. There is also a hidden layer of processing that kind of connects between each major component unit, and that is what basically is the processing part of the model. So, you can see the model here in this figure. You will see that there is content, meaning, and orthography and phonology. So, context is kind of at the top, but then you have meaning, that is the semantic units, orthography and phonology. You will see each of these units have a layer of hidden have a hidden processing units in the middle, which basically will carry out all the processing. And if you look at the hidden units, there are 100 to 200 hidden units with respect to between context and meaning, and then there are 400 orthographic units and 460 phonological units. So, basically here in B you have a more specific mechanism for generating pronunciations. So, if you look, part A is the entire model, part B is the part of the model that is used to create pronunciation. So, how many units will be required for analyzing orthography to phonology? Now, basically how does processing happen in this model? Once the model encounters the visual input, it leads to activity in the orthographic units, which then leads to activity in the hidden units that govern the activity in the phonological units. So, as soon as the activity is registered at the orthographic units via the hidden units, it will start creating some activity in the phonological units part, leading to the naming response, leading to generation of the sound code. Every word is represented as a distributed pattern of activation across this entire network. Learning basically in this model involves modifying the weights through experience in reading aloud. Say for example, the more and more experience that the model gains, the more basically it modifies the weights. It basically learns, okay, how many units I have to put in the orthography part, how many units I have to put in the phonology part, how many units I have to put in the meaning part, and these number of units will probably be adjusted with respect to the model's performance. So, say for example, if the model is performing purely, you can adjust the weights to lead to gradually better performance, and once the model is giving near perfect performance, that is sort of the resting count of, okay, this is the actual number of units that is used for this particular representation. Moving further, Each processing unit is connected to others, so that when one unit is activated, it can influence the activation of other units. So for example, if you are hearing words or if you are reading words, in this case reading words, as soon as you there is some activity registered in the reading part, in the visual part, that kind of will create activity in the orthographic part, and as soon as some activity is registered in the orthographic part, both the meaning and the phonology part will start receiving some activation. Okay. So, and to begin with, say for example, the connection weights between all of these units, the orthographic and the phonology and the meaning units, are sort of randomized, but they are adjusted with practice or experience. Say for example, in the first iteration, in the first 100, after first 100 trials, the model gives up 40% correct meanings, but 40% correct visual recognition, but 60% incorrect. So you kind of again adjust the weights, you try and steer it to getting the maximum correct performance. Now, what do you actually mean by practice? Practice is basically the training trials that you expose the model to. You kind of put some randomized weights and you give the model the input, and you kind of expect correct recognition from the model. Usually in the beginning the model will not really be able to give you correct performance, but you kind of do the process iteratively. Gradually the model kind of figures out what are the correct weights using which I can reach the sort of a correct pronunciation. So these training trials, usually around up to 1,50,000, basically are used for the model to learn what are the processes, what are the things that I need to do in order to get to the correct recognition. Okay. So after activation has spread through the entire network, the pattern of activations of the output units are compared to the correct output. This is the pattern of activation of the output unit. This is what my result is, and you correct compare with the actual result, and you try and match this. And this kind of the weights in the model keep getting adjusted, and the output units keep getting different kinds of outputs, and it keeps getting compared with the correct output. As soon as this comparison is closer and closest, that is how the number of units here will start getting sort of fixed. Okay. So these weights are therefore adjusted to get to the best performance of the model. Now, one of the advantages of this kind of simple architecture of the single root networks model is that it kind of resembles human performance very well. The data and the output and the response patterns of the single root network models is found to be closely matching the performance output of the actual models. Now, we can sort of try and evaluate the performance of this model as well by various ways. One of the ways is to look at the phonological error score. Say for example, how well or how correct the phonological representation that the model has come up with matches the actual correct pronunciation. Now basically how do you do it is you differentiate or you compare the model output with respect to pronunciation with the actual pronunciation, and you indicate basically whether the model has pronounced a particular word correctly or incorrectly, and basically the difference in the model's pronunciation and the actual pronunciation gives you an idea of the phonological error that the model has made. If the phonological error score is minimal, it means that the model is performing alright. If the phonological error score is slightly larger, you probably need to adjust the weights in order to get the model closer to the actual pronunciation. Now what happens after the model is trained for a lot of time? It's been, say for example, 500,000 trials or something like that, and the model has started giving better output. So basically what happens is after training the error scores would be found lower as compared to the correct when compared to the correct output. Also the model was found to generate lower scores for words that it learned more. So the more practice it has with particular words, the better it gets with reading those particular words. Also the model kind of interestingly produced regularization errors like the humans would do in the for mostly low frequency words, which it would have got less time to learn with. Also it was found that the model produced longer response times for irregular words. So it seems that the model is kind of using the phonological activations in a slightly more primary sense, and that is why it is leading to these kind of errors. Also model responded to non-word like stimuli, say for example brain, BRANE, it found it slightly harder to reject those words, much like the humans do. It's following a process which is very similar to what the humans kind of do. Now you've seen the dual root cascaded models and you've seen the single root models. Now what we can do is we can compare the two models on different kinds of word recognition phenomenon. Let us look at, say for example, the orthographic neighborhood effect. Now orthographic neighborhood is basically specifying, say for example, if there is a word, how many letters you can change to create another word. Say for example, if there is a word called book, you can change just one letter to form another word look, or another letter took, and two letters to lead it to shook. So for example, the idea is the number of changes you can do to a particular word to create another word basically defines how many neighbors sort of it has. So if you can change one, and how many letters, how many different words you can come up by changing just one letter, how many different words you can come up with changing two letters, how many different words you can come up with changing three letters. This is the orthographic neighborhood of this word. The lowest number of changes needed and the more number of words you generate is sort of, it gives you an idea about how many neighbors that this word have. According to Coulthart's neighborhood metric, Max Coulthart had pointed out, had devised a way to measure the neighborhood of particular words, and it found out that a word's neighborhood basically consists of all words that can be made by changing just one letter in that word. So if you can just change one letter and create, say for example, 10 words, then 10 is the neighborhood size of that word. If you can create one letter and create 1000 words, then 1000 is the neighborhood size of that word. And different words may have small versus large neighborhoods, so that is also there. And in word recognition experiments, it has been found that words with large neighborhoods are slightly faster to recognize. Now there are also things like consistent or inconsistent neighborhoods. Say for example, all words having consistent pronunciation, so book, took, look, shook have consistent pronunciations, versus say for example, there could be inconsistent neighborhoods also. Say for example, the words like mint, tint, but then you have another neighbor like pint. Okay, so then they have the neighbors can have different pronunciations, and that would be referred to as having an inconsistent neighborhood. Interestingly, it has been found, say for example, words with large neighborhoods are recognized earlier. And why would that happen? It's basically because letters that activate large neighborhoods will lead to more units sending activations from the orthography to the phonological units connected to that neighborhood, leading to faster reading recognition and naming times. Also, it has been found that words with consistent neighborhoods are also read faster than those with inconsistent neighborhoods. You might wonder why. It's basically because in consistent neighborhood, all members would point to similar pronunciations, versus in inconsistent neighborhoods, all members will start pointing out to different kinds of pronunciations that will lead to difficulty and slowing down. So words with consistent neighborhoods therefore are read faster as compared to words with inconsistent neighborhoods. Also, one of the more important effects that you kind of need to explain is the frequency effects. In the single root models, basically what you can do is you can adjust the connection weights with high frequency words slightly better as compared to the low frequency words. So because the model comes across the higher frequent words more number of times, it knows, or it learns to read those words better. It learns to adjust the connection weights for those words better as compared to less frequent words, and that is why the high frequent words will also be recognized faster and with less error in single root network models. This is all from me about the kinds of models of word recognition that we have read, and I'll talk to you about a different process in the next class.